皆様、こんにちは。僕はアメリカのチェラパラのマックワータージョンです。2年間、日本に住んでいました。1997年から8年まで、マンジュで働きました。たくさんのことを学びました。と、たくさんの親切な日本人を会いました。でも、日本語は難しいですから、英語で話しましょう。Okay. So thank you very much. Nice to be here. I'm going to talk about two different projects that TerraPower is using right now. The first is Natrium, and the second is Molten Chloride Fast Reactor, or MCFR. So first is Natrium, which is generated by TerraPower and GE Hitachi. So the Natrium plant is designed to use the best practices from sodium fast reactor knowledge, as well as leveraging from solar power knowledge with molten salts. The main thing is we're trying to decouple the nuclear side from the power generation side. In traditional nuclear plant construction, the power generation and the nuclear is all put together at the same time, or has to be constructed at the same time in a way that interferes. Kinjo-san. And so we're trying to decouple that with two different portions. I'll show that on the next slide, but a key aspect is high thermal efficiency, 41%, and the simplicity is also important, rapid construction, and very specific designs for staffing. The integral sodium fast reactor is the key, and I'll have a nice slide showing that in a minute. The distributed nuclear facility layout, that's what I'm talking about from the decoupling of the heat production and the electricity production. So that's decoupling. Advanced one-through fuel system. Right now, that's TerraPower's going in philosophy is once through. And we have the energy storage. This is our nominal energy output, 345 megawatts electric with a reactor. The reactor operates full power 24/7, but the salt storage system absorbs heat when we're not interested in selling electricity as much. So when, for instance, solar and wind are producing a lot of energy, we will back off and we will save our heat in the form of the salt storage system. And then when solar and wind are less active, we can produce up to 500 megawatts electric for up to 5.5 hours. So this is a general layout of the plant. Here is the reactor building and fuel building, and over here is the molten salt tanks and the steam generating system between the hot tank and the cold tank. And then we have the steam turbines and heat rejection over here. And then there's just various other auxiliary buildings. Let's see. Yeah. So this just shows the boundary between the nuclear boundary and the non-nuclear boundary. So the bottom line is we can be constructing, we can be constructing the nuclear and the energy conversion at the same time without interfering. Another aspect is because they're decoupled, this is the only coupling between the nuclear and the non-nuclear, the salt pipe coming from the reactor going to the steam generation. And so another key is the quality control side. On the nuclear side, the nuclear QA is higher than standard industrial QA on the steam generating side. So there's also a cost savings associated with that. Here's a general cross-section of the plant. Here's the reactor, and we have intermediate sodium piping coming down to an immersed intermediate heat exchanger. Okay, so the sodium comes out here into a salt to sodium heat exchanger, and then the hot heated salt comes and goes to the storage tanks. And then the return salt comes in, exchanges heat again, and the cooled sodium comes down and back into the reactor. Okay, we have we have spent fuel over here, which will be water. So there will be a washing facility to clean. When we pull fuel out of the reactor, it'll have some residual sodium on it. We'll clean that off, and then we'll put it in the spent fuel water pool. Okay, some of the key features of the Natrium program is the pool-type metal fuel with molten salt energy island, simplified response to abnormal events, so you have reliable shutdown, reliable reactor shutdown. We have very closely inherent natural circulation system. Sodium's very good in terms of natural convection of heat from the core, and then that is tied to the ultimate heat sink, which is air, and through piping and heat exchange. But so there's low pressure functional containment and no reliance on the energy island for safety functions. There's no safety related control systems needed to transition to natural circulation of all decay heat. And we're leveraging our experience in the US from EBR1, EBR2, fast flux test facility, and transient reactor experiment at Idaho National Laboratory. And the safety characteristics for metal fuel have been demonstrated in EBR2 and FFTF. So we are very strong very strong advocates of metallic fuel. Control, we have a run back system that would kick in to avoid a scram, but if there is a scram necessary, it's gravity driven control rods. And we have good, strong negative temperature and power coefficients of reactivity, so inherently stable with increased power or temperature. And the cooling is, like I mentioned, the sodium naturally circulates and connects with air on the outside of the vessel to connect to the natural draft air cooling system. The containments here are set, assuming the containment of problems includes low primary and secondary pressure, so the vessel can be not as thick. We have sodium binds certain radionuclides effectively if there is a breach, and there are multiple radionuclide retention boundaries. So the program roadmap, we started off, so in the US Legacy program, PRISM traveling wave reactor, which was developed at TerraPower originally back in 2007, when we started looking at the traveling wave reactor. We've leveraged all of that information. PRISM is GE Hitachi, TerraPower is TWR, so we kind of mated those two to come up with the Natrium program. And that's happening now. We're looking at deployment of the demonstration project, which is, I mentioned 345 megawatts electric nominal, 500 megawatts electric peak, and looking at doing that in the 2030 timeframe completion. Beyond 2030 plus, we're shooting for a 3-year construction interval plus the energy storage and peaking capability. In the 2040 time period and plus, we're looking at other benefits. This right here is a picture of large canisters of depleted uranium. The original traveling wave reactor concept was called a breed and burn, depleted uranium breed and burn, and that is still a goal of the overall TerraPower reactor program, is achieving breed and burn long term, and that is to get most efficient use of the fuel, including the plutonium. And then we're looking at the potential for plutonium disposition and recycling, and as with a higher fuel temperature, we can get better use of potentials for process heat. Okay, for the fuel qualification path, this is very important. Obviously, we have the fast flux test facility fuel. We have actual pins that we have possession of, or that we can get access to. We have the material HT9, which is what we're using for cladding, which has excellent low swelling properties in a high flux, high fast spectrum, high energy spectrum environment. The advanced test reactor test compares historic and new sodium bonded fuels. We have transient testing of the previously irradiated pins, and then we'll have ultimately the Kimmerer plant in Wyoming come to fruition. That's type 1. Type 1B fuel is not sodium bonded. It is annular, so that it will, when the fuel swells, it will occupy the full volume of the fuel pin. But we'll be doing ATR, advanced test reactor tests. That's in Idaho as well, ATR. Transient testing, lead test assembly from the Natrium plant of these fuels, and then we will have the commercial reactor series. So you can see that host and advanced fuel testing activities will be performed in parallel to support the project and commercial reactors. Okay, earlier this year January was a busy year. We had, to the NRC, we had a topical report for principal design criteria and fuel and control assembly qualification topical report. And we had what we call design review 1 of the overall plant design, going from transitioning from our formal conceptual design to preliminary design. We've placed contracts for the IHX, for the sodium pumps, and are in the selection process for those. HT9 fuel assembly test articles. These are all supply chain development issues, and they've been there's going to be some panel discussion, I believe, about supply chain later on. We started drafting the PSAR, and we're doing operations training and program and procedures for operations. Future needs include instrumented test reactor positions, and turnaround capability for the post-radiation exams is going to be a key thing to try to accelerate. Fabrication capabilities of porous fuel and transient testing on commercial lead pins. Those are our main future needs. Okay, next is our molten chloride fast reactor program. Because we have a molten salt with very high boiling or dissociation temperatures, we have low pressures. Oops, let's see, wrong one. And because it's just a salt volume, not solid fuel in pins, we believe the cost of the fuel fabrication can go down. with online refueling possibilities, you don't have to shut down to do some refueling, so the availability of the plant, the operating tempo can be higher in principle. The temperature is higher, so we're talking about 650 C and higher temperatures, so it's a very high-grade heat with potential for industrial process heat. Because it's a liquid fuel with a very strong negative temperature coefficients, we believe safety can be enhanced. We're only going to be using denatured fissile material, so it's not in a highly usable weapons form at all. It's in denatured salt form, and we can use actinides and lanthanides, so it's very unattractive from a weapons proliferation standpoint. And the fast spectrum will give us little reprocessing need. The plant that I'm talking about here, this is a concept plant for the molten chloride fast reactor. Here is this is the reflector region which defines the core. So when you have a fuel of a certain concentration inside the reflector, and you have a neutron source, you will have a sustaining chain reaction, but it's liquid and we pump it. This is a pump. These are pumps distributed along the top here, pushing, pulling from the top of the core and pushing through a heat exchanger and then back into the core. So the fuel circulates in this fashion, and the fuel has very inherent strong, the density changes very strongly with temperature, so it's very effectively negative temperature coefficient. The fuel form is a uranium chloride, sodium chloride eutectic mixture, 6733, fueled with HALEU at about 20% enrichment, fast spectrum, and like I said, the temperatures are high. This up here is a layout of the plant with the vessel and core here, heat exchanger pipes coming up, various other tankage for salt storage, and here's energy conversion to steam over here to a steam turbine. Okay, the technology development roadmap. We're starting off with separate effects tests. We have made many materials test loops with a variety of materials and a variety of salts. And so we believe very early on in an aggressive testing program and to try to get data as much as we can. Separate effects tests also include other things related to chemistry control. The culmination of this is what we call an integral effects test facility, which is being commissioned right now at our laboratory in Everett, Washington, north of Bellevue, north of Seattle. This is all going towards the development of what we call our molten chloride reactor experiment, or MCRE, which is based at 150 kilowatts thermal. I'll talk more about the MCRE here in a little bit. There's possibilities. We can go in a couple of directions here. We can go to a plutonium burner prototype in the 10 megawatt thermal range, or we can go, our baseline is to go to a demo with the 3 to 180 megawatts thermal, but there's also this option to consume plutonium in a smaller burner reactor. And then this can culminate in two separate paths: a small to mid-scale product, 30 to 300 megawatt electric plant, or a grid scale up to 1,200 megawatt electric plant. And again, this is the basic concept of the plant. And this is the time frames. 2026, 2027 is when the MCRE, we hope, is going to be up and running. And then you can see the other time frames here. Okay, so the MCRE is going to be built at the Idaho National Laboratory Zipper, zero power physics reactor, was in this building right here at the old Argonne West laboratory. And let's see if there's, here's Argonne, the old Argonne West, which is now part of INL. There was EBR2, and here is the Zipper building. And it is now called Lotus, Laboratory for Operations and Testing in the US. And so the MCREE mission and objectives to measure key physics phenomena and other hypotheses about how the liquid fuel, circulating liquid fuel, will behave dynamically. So objectives include achieving criticality with the first fast spectrum, not just the first fast spectrum molten salt reactor, but the very first fast spectrum circulating fuel facility, circulating fuel reactor. That'll be a first in the world as far as we know. Reactor physics and kinetics parameters. One of the key things about a circulating fuel is that the effective delayed neutron fraction is a function of the flow rate of the fuel. So as some delayed neutrons leave the core, the beta effective decreases. So it's a key dynamic parameter that has to be understood. Fuel loading and handling is another objective. Supply chain development for molten salt components, and that's always big. And then a risk-informed, performance-based licensing framework is also a key. Here's the basic reactor design for the MCREE. Here is the vessel with that will contain the liquid fuel. Here is the reflector assembly, which is bricks of magnesium oxide. And the circulation path will go from the top through the pump here to this flow loop through a Venturi flow meter and back into the core. A major thing that's missing here that we do not have in this system is a cooling system. So essentially it is a 150 megawatt thermal design, but we have no way of removing 150 megawatts thermal of heat. And so it's going to be very interesting to operate the reactor. It will end up not operating at 150 megawatts thermal very much. Probably more around the 10 to 20 kilowatts range will be at steady state power. But we may be able to get transient powers up to 150 kilowatts thermal. And just some more details of the plant layout and some instrumentation is on the next slide here. Here's the design parameters. Like I said, design temperature, design power, 150 kilowatts. 700 C is the design temperature, but our operational limit will be 650 C. Design pressure, 500 kilopascals. Gauge, salt flow rate, 25 to 100 kilograms per second. Temperature I mentioned. Fuel salt melting temperature is 523, so we have about a 75 C margin between operations temperatures and fuel freezing, which we don't want to ever have. We have about 950 kilograms of fuel salt, and the reactivity control is B4C. Let's see, just some instrumentation layout here. Because it's a first-of-a-kind reactor, we're going to have, it's going to be very heavily instrumented, and that's just what I'm trying to show here. And just some other nuclear instrumentation details. Because we're looking at measuring different key reactor parameters, physics parameters, that justifies the need for all these different instruments. And then we'll have an americium beryllium startup source. Okay, we're going to have a mock-up at our Everett lab, and we will be we'll be learning a lot about how to operate a salt facility. We're already learning a lot with our integral effects test, but actually trying to do it like we will actually be operating a reactor will be very informative. We won't be using fuel in the mock-up. We will be using sodium chloride, magnesium chloride, or what we call flush salt, and we can blend to get the melting point to be what we want it to be. And there's other testing occurring. These are separate effects tests, and okay. We have what we call the two-tank test for fittings and instrumentation. We have a thermal management for the magnetic coupler, and this is a pump test for the bearings. And then our alloy 625 grade 2 properties testing. Here's just a basic photograph of how nickel alloys have performed compared to iron alloys with respect to corrosion in flowing liquid salts at very high temperatures. So we've tested uranium chloride, potassium chloride with alloy 625 at 750 C for about 6,000 hours. And we have good results, so we're very enthusiastic about that. This is a small little facility here. I'll skip that for now. We've got another facility, but here's the integrated effects test. And just a lot of piping, a lot of pumps to demonstrate these key features over here. And that's all I have to talk about. Any questions?
ありがとうございます。ではご質問ございましたらお受けしたいと思います。挙手でお知らせください。いかがでしょうか。ございませんか。皆様大丈夫でしょうか。それでは、本講演終了させていただきます。ご講演をいただきましたマックワーター様に大きな拍手をお送りください。ありがとうございました。Thank you very much.